Alright. So before beginning, does anyone have any questions about this week's lecture or anything in general? Okay, I think no, then we can get started. Okay, so today's problems will also be based on basic counting and proving some identities like last week. So let's look at the first question. So the first question asks to show that for any two integers n and k, this thing is true. So k choose k plus 1 choose k and so on up to n choose k is equal to n plus 1 choose k plus 1. And we have to show this for all okay. So we have to show this identity for all n greater than equal to k greater than equal to 1. Okay. So what we are going to use is induction. We are going to do induction on n. So first of all, we are going to fix some value of k. And now when k is fixed, so now n is the only variable. So we are going to do induction on n. So what is the base case? The base case is when n is equal to k. So when n is equal to k, what is the LHS? It is just k choose k, which is 1. And what is the RHS? RHS is again 1. So in the base case we are done. When n is equal to k, we are done. So now we are going to assume by induction that this thing is true for some value of n. So yeah, so now we have to show this when n is equal to n plus 1 for for n plus 1, what is the LHS? This thing, right? When n is equal to n plus 1, this is my LHS. Now by induction hypothesis, we know that this sum is equal to n plus 1 choose k plus 1. By induction we know this. So we can replace this by this thing, right? And now this is a very standard identity for NCR. So this thing is nothing but n plus 2 choose k plus 1. Why? Because you have to recall the identity. Right, this is a very well known identity for NCR. So using this we get that the sum of these two terms is equal to this term, and this is what we needed to show. So when n is equal to n plus 1, the sum should be equal to n plus 2 choose k plus 1, and that is what we have shown. So hence by induction we are done. Okay, so this was a pretty simple question. So I hope it's clear. Okay, so if there are no questions, we can move on to the next question. Okay, so what does this question say? This we have to find the number of permutations of a deck of 52 cards where all cards of the same suits are together. So what does it mean? So we know that out of 52 cards there are 4 suits, that is diamond, heart, spades and clubs. There are 4 suits and each suit has 13 cards each. So what we are required to find is in how many ways can we arrange these 52 cards so that all cards of hearts are together, all cards of diamonds are together, all cards of clubs, and similarly for spades are together. So how many such permutations are possible? Okay. So now, as I said, there are 4 suits, right? So all cards belonging to a single suit have to be placed side by side, and for now we are not worried about the order inside the suits, but now the first condition is that all cards of the same suits have to be together. Okay, so then if we just focus on the suits, there are 4 factorial ways of arranging the suits on a straight line, right? So okay, so in 4 factorial ways we can arrange the suits. Now inside each suit, so now fix one of these 4 factorial arrangements. So what do we have? Let's say the arrangement is heart, club, spade and diamond. Suppose this is one possible arrangement. So then now inside the 13 cards which belong to hearts, they can be arranged among themselves in 13 factorial ways, right? Similarly, for clubs, the 13 cards which belong to the club suit, they can again be arranged in 13 factorial ways. And so for each such arrangement we get 13 factorial to the power 4 possible arrangements of this. Okay, so then what is the total number of possible ways? This thing, right? So 4 factorial for the suits, and then inside each suit we have 13 factorial. So this is the total number of possible ways. Okay. Okay, so I hope this is clear. Okay, so the next question is, we have to count the number of divisors of 10 to the power 10. So how many, so this is some huge number, we have to count how many divisors does this number have. Okay, so how do we do this? So first of all we need to factorize this into prime factors. So we have this. So here 2 and 5 are primes. So this is the prime factorization of this number. So now once we have this decomposition into primes, what will any divisor look like? So right, so here, so since the prime factorization is 2 to the power 10 times 5 to the power 10, so any divisor must be something like 2 to the power a times 5 to the power b, where a is some integer between 0 and 10 and b is some integer between 0 and 10 again, right? So I hope this is clear, because anything which divides 10 to the power 10, it must be composed of some power of 2 and some power of 5, and the power of 2 should not exceed 10, and similarly the power of 5 should not exceed 10. So we just need to count how many such compositions are possible. So as we see, there are 11 possible values of a from 0 to 10, and similarly 11 possible values of b from 0 to 10. And for each such pair a comma b, we'll get a unique divisor of this number 10 to the power 10. So hence, what is the number of divisors? Okay, so there are 11 square, that is 121 many divisors of this number, right? So in general, whenever you want to count the number of divisors of some number, you have to first do the prime factorization of that number, and then you have to check, you have to write any divisor as a product of primes, as a product of the prime divisors of that number, and then check how many such exponents are possible and multiply them. Okay, I hope it's clear. Okay, so if there are no questions, we can go to the next one. So this says, how many integers larger than 10,000 have distinct digits and does not contain the digits 5 or 3? So we have to count how many such numbers are there, each of which is more than this 10,000, and it must have distinct digits, that is, a particular digit should not repeat, and it should not contain the digits 5 and 3. Okay. So then, such an integer, since it has to be larger than 10,000, it obviously has to be at least a 5-digit number, right? So it has to be at least a 5-digit number, and now since it has distinct digits and also both the digits 5 and 3 do not appear, so then what is the total number of possible? Is my screen visible? Can anyone confirm? I think I lost my connection probably. Hello, can anyone please confirm whether my screen is visible? Okay, I think I had lost connection. There was some connection issue from my end. Yeah, I hope my screen is visible now, right? Okay. Yeah, so as I was saying, so we have to count the number of integers larger than 10,000 which have distinct digits, and it should not contain 5 and 3. So as I said, since the number has to be larger than 10,000, it must be at least a 5-digit number. That is one condition. And secondly, since it has distinct digits and 5 and 3 do not appear, so then what is the maximum possible number of digits in that number? It is 8, right? Because there are 10 digits, 0, 1, 2 up to 9, and we know that 5 and 3 do not appear, and all the digits have to be distinct. So the maximum possible number of digits can be 8, right? So what can we say? Yeah, you want to ask a question? Go ahead. So, Jayabal, you want to ask some question? Please go ahead. Okay. Okay, so we have this. So it must at least be a 5-digit number because it has to be more than 10,000, and it can have at most 8 digits because it cannot have 5 and 3. So there are 4 possible number of digits: 5, 6, 7 and 8. So individually we have to count how many such numbers are there. So first let us count how many such 5-digit numbers are there. Okay. So there are 5 digits. Now what are the possible digits for the first position? So the first position can take any digit except 0, 3 and 5, right? Because obviously if 0 is the first digit, then it will not be a 5-digit number and it should not contain 5 and 3. So therefore except 0, 3 and 5, any other digit is possible. So there are 7 possibilities for the first digit, right? So there are 7 possibilities. Now once we have fixed this digit, how many possibilities are there for the second digit? Again, suppose we have fixed the digit, let's say a, in this position. Then except a, 3 and 5, all the other digits are possible for this, right? Once we have fixed a, suppose a is equal to 6. So then this position, the second position, can take any value other than 6 and 3 and 5. So again there are 7 possibilities. Now once we have fixed the second digit, there are 6 possibilities for the third digit, then 5, then 4, right? Since the digits have to be distinct. So then what is the number of 5-digit numbers? This thing. Okay, so next we have to count the number of 6-digit numbers. Okay, so again, how many possibilities are there for the first digit? So the first digit can be anything other than 0, 3 and 5. So again there are 7 possibilities. Now again, as before, once we have fixed the first digit, there will be 7 possibilities left for the second digit. So again, suppose the first digit is a, then the second digit can be anything other than a, 3 and 5. So again there are 7 possibilities. And similarly, the third digit, there are 6 possibilities, then 5, then 4 and finally 3. So hence okay, so for 6 digits, this many number of possible numbers are there. Okay, and in exactly the similar way, we can count for 7 digits. What will be the answer? So if we do in exactly the same way, again it is going to be 7 into 7 to 6, 5, 4, 3 and finally 2. Okay. 1. Okay, and then finally you just have to add this. So these are simple calculations which you can find the value of this. I am not doing that. So this product, all these products you can find easily, and then you have to just add them. So okay, just adding them will give you the answer. But what's important is the method. So first of all, we found how many digits are possible, and then we did some case analysis, some very simple case analysis. Okay. 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 So let's move on to the next question. So this says that in how many ways can 5 boys and 5 girls be seated alternately around a round table? So we have 5 boys and 5 girls, and we have a round table. There are 10 possible locations on around the round table. So the question is, in how many possible ways can 5 boys and 5 girls be arranged on the round table? And the constraint is that they should be seated alternately, that is boy, girl, and so on. Okay. So let's say this is the round table. So let's say we are going to number the boys by B1, B2, B3, B4, B5, and similarly the girls to be G1, G2, G3, G4 and G5. So let us consider the positions of the boys. So here there is going to be, okay. So the green positions are for boys, and let's say the red positions are for girls. Okay. So now there are 5 boys and 5 possible positions for the boys marked in green. So in how many ways? So let's forget for some time, let's forget that it is a circle. That we'll take care of later. So now there are 5 boys and 5 possible positions of the boys. So in how many ways can we arrange them? It's 5 factorial, right? Okay. Similarly, since there are 5 girls and 5 possible positions for the girls, how many ways can we arrange the girls? It's again 5 factorial. So but now we have to consider that this is a round table. So basically any cyclic permutation we have to count only once. So what does that mean? For example, let's consider one particular arrangement. Suppose we have B1, okay, suppose this is one particular arrangement where we have B1, G1, then B2, G2, B3, G3 and so on. So now this arrangement is exactly the same as this particular arrangement. So right, it's just a cyclic shift, and 2 cyclic shifts, since it is a round table, these are cyclic shifts are the same. So these 2 permutations are in fact the same, but we have considered 5 factorial and 5 factorial. So then basically what we have done is we have considered these 2 permutations to be distinct. We have counted them. So now we have to count that for a particular arrangement how many such overcounting we have done. So then if we fix this particular arrangement, so how many such possible cyclic shifts are there? So B1, here we had fixed the position of B1 to be here. So the positions of B1 can be here. So if we move B1 from here to here, we basically get this one, right? Again, similarly, B1 can also be shifted to the position of B3 and the whole thing can be rotated. Similarly, B1 can be moved to B4 and B1 can be moved to B5. So, for every such arrangement, what we have done is we have counted that particular arrangement 5 times. So, for if that is yeah. So what we have done is for every possible arrangement, we have overcounted that particular arrangement 5 times. Okay. So hence the total number of possible ways okay. So this is my answer, 5 factorial times 4 factorial. If the problem was just to arrange the boys and girls on a straight line, then this was my answer, 5 factorial times 5 factorial. But now since they are to be seriated on a round table, so cyclic shifts are basically the same. If we can obtain one permutation by a cyclic shift of some other permutation, then those two should not be counted twice. So here, if we do 5 factorial times 5 factorial, we have basically counted each arrangement 5 times, right? So hence we have to divide by 5, and therefore this is my answer, 5 factorial times 4 factorial. Okay, I hope there are no questions. Okay, let's move on to the next question. So what this says is that there are 20 people who need to be and we have to arrange these 20 people in a queue in front of a counter, and each of them want to buy some item which is worth 100 rupees. So now initially the counter has no money, and we are given the information that exactly 10 out of these 20 people have 100 rupee notes and the remaining 10 have 200 rupee notes. So the question is, find the number of ways in which they can be arranged in the queue so that no one has to wait for change. So what does this mean? So initially the counter has no cash. So the price of the item is 100 rupees and exactly 10 of them have 100 rupees and exactly 10 of them have 200 rupee notes. So now, since the counter initially does not have any cash to begin with, so if the first person in the queue is one who has a 200 rupee note, then he has to wait for change, right? Because he is giving 200 rupee, he has to receive 100 rupees. So then he has to wait for someone with a 100 rupee note, which that person will give to the counter and the counter will return him. So that is not what we want. We want that each of these persons who have 200 rupee notes, they should not have to wait for change. So subject to this constraint, in how many ways can these 20 people arranged in the queue? That is the question. Okay, so I hope it's clear. Yeah, okay. So for simplicity, so instead of working with 100 and 200, let's just scale it and make it 1 and 2. It doesn't make any difference, right? So let's scale it. Okay, so we can assume by scaling that the price of the item is equal to 1 and each person either has 1 rupee or 2 rupee, and the question remains the same, that in how many ways can I arrange them so that no one has to wait for change. So what does that mean? That in any such arrangement, when will this happen? So let's say consider one such arrangement. So suppose 1 is there, then 2 is there, and then again suppose a person with 2 rupee note is there. Then what? So the first person Yeah, so the first person, this guy does not have to wait for change. That is very clear. Now, when the second person comes, the counter already has a 1 rupee note and he can give it. So the second person does not again have to wait for change. But now, the third person, he has to wait for change, right? Because the counter no longer has any 1 rupee note. So this is not allowed. So in general, when will this happen? That at any point, the number of 1 rupee, the number of people having 1 rupee should be greater than or equal to the number of people having 2 rupees, right? So suppose at any point in that arrangement, if there is some point such that the number of 2 is more than the number of 1, then some person has to wait for change, right? So this condition can only be satisfied if and only if okay, so this is what we want. We have to, so any valid sequence should have this property that at any point the number of people who have 2 rupees should be at least the number of people that have 1 rupee. Okay, then no person has to wait for change. So then this looks very similar to the Catalan number setting that we had considered last week. So how do we draw a connection to the Catalan number setting? So what do we have in the Catalan number problem? So we have this grid, we have this line y is equal to x, we start from the origin, we have to move to a point 10, 10 using lattice paths, and the constraint is that we should at no point cross the line y equal to x. So the path should be something like this, right? So how do we draw a connection with our problem? So let's say, what do we do? So now there are 20 people in total, 10 of them have 1 rupee and 10 of them have 2 rupees. So let's say whenever there is a person with 1 rupee note, we move to the right, okay, and whenever there is a person with 2 rupee note, we move up, okay. Then this condition that we need, that is the number of people having 2 rupees should be at least the number of people having 1 rupee. This is exactly in bijection with this situation, right? At any point, so what are we doing? Okay, suppose we do this, then what do we want? If we plot this on a graph, plot this on this graph, on this grid, then what are we doing? We are moving from 0, 0 to 10, 10 using lattice paths, and at no point should we cross the line y is equal to x. So this thing, that at any point the number of people having 2 rupees is at least the number of people having 1 rupee, this exactly says that we have to move from 0, 0 to 10, 10 using lattice paths, and at no point we should cross the line y equal to x, right? Okay. Okay, and this is exactly C10, the 10th Catalan number. So and what is that? 1 by 11 times 20 choose 10, right? 1 by n plus 1, 2n secant. So it's this. But we have to be a little more careful. So now, so this is the number of such paths, number of such possible paths. Okay, I think I'd lost my connection probably. Wait, let me reshare. Yeah, I think now my screen is visible. So yeah, so this is my 10th Catalan number, that is 1 by 11 times 20 choose 10. But now suppose we have fixed this sequence. So once we have, so what is a sequence? It is just a sequence of ones and twos. So there are 10 ones and 10 twos in this sequence. So now once we have this sequence, then the positions corresponding to 1, they can, so those 10 people can be arranged in those positions in 10 factorial ways. So right, so there are, in this sequence there are 10 ones and there are 10 people who have 1 rupees, and those 10 people need to be placed in these 10 positions which contain 1. So there are 10 factorial ways of doing this. So the number of ways of this is 10 factorial. And similarly, the positions which have 2, the persons having 2 rupees need to be placed there. So again there are 10 factorial. So okay, so then what is the total number of ways? This thing, right? So this is my C10 times 10 factorial square, and this you can slightly simplify, 20 factorial by 11. So because 20 choose 10 is nothing but 20 factorial by 10 factorial times 10 factorial, and that is going to cancel out with this 10 factorial square. So ultimately we'll be left with this thing, 20 factorial by 11, and this is my answer. Okay, so this connection to the Catalan number setting, this was the main catch in this question, that the number of possible sequences exactly corresponds to the number of lattice paths from 0, 0 to 10, 10 without crossing y equal to x. This was the main catch that you need to have. Okay, so I hope it's clear. Okay, so let's go to the next question. So this says that we have to show that for all n greater than equal to 1 and r greater than e, this inequality is true. N factorial is more than n by r to the power n. And we can use the fact that this sequence n by n plus 1 to the power n, this is a monotone decreasing sequence and converges to 1 by e. Okay, so yeah, so we need to show this inequality, and we can use this fact, the fact that n by n plus 1 to the power n, this sequence, it is a monotone decreasing sequence which converges to 1 by e as n goes to infinity. Okay, so then since we need to show this inequality for every r more than e, it suffices to show this thing, right? If we are able to show this thing, then since r is greater than e, so this will directly imply that n factorial is more than n by r to the power n. Why? Because r is less than e. So n by e to the power n is lower bounded by n by r to the power n. So we'll just show this thing. Okay, we are just going to show this thing, that n factorial is more than n by e to the power n. And how are we going to show this? We'll use induction. Okay, so what is our induction hypothesis? Let's say this is my induction hypothesis. So we define this quantity n factorial by n to the power n. We call this number as t of n. So what we need to show is t of n is at least 1 by e to the power n, right? So this will imply that n factorial is more than n by e whole to the power n, right? So my induction hypothesis is Tn is greater than 1 by e to the power n for all n greater than equal to 1. Okay, so then what is the base case? When n is equal to 1, what is t of 1? Right, so when n is equal to 1, this inequality is trivially true. The LHS is 1 and the RHS is 1 by e. So 1 is more than 1 by e. So this is fine. So now let's assume that this to be true for n. Okay, and now we have to show this thing for n plus 1. So what is Tn plus 1? Tn plus 1 is nothing but this thing, right? So then suppose we take the ratio suppose we consider this ratio. So what will we get? So sorry. So this, if we try to simplify, so we get this thing, right? So the ratio Tn plus 1 by Tn, this comes out to be equal to n by n plus 1 whole to the power n. But we know that this sequence n by n plus 1 whole to the power n, we know that this is a monotone decreasing sequence which converges to 1 by e. So what does this mean? That this quantity n by n plus 1 to the power n, it is always lower bounded by 1 by e, because this sequence, it is a decreasing sequence. So it starts from, so when n is equal to 1, its value is equal to half. So it starts from half and then it monotonically decreases, and when n goes to infinity, this reaches asymptotically 1 by e. So what does it mean? That for any finite n, any particular value of n, this number lies in the range 1 by e to half. That is, it is always more than half, because 1 by e is the limiting value of this sequence. So hence this quantity is always more than 1 by e. So once we have this, so what do we get? We get this thing, Tn plus 1 is at least Tn by e. But using induction, we had assumed that Tn is at least 1 by e to the power n. So if we put it here, this product is going to be at least 1 by e to the power n plus 1, because Tn is at least 1 by e to the power n. Okay? So hence we are done. By induction we are done. Okay, so we have shown that n factorial is more than n by e whole to the power n for every positive integer n. Okay. Okay, so let's look at the next question. So this says to find a closed form expression for these two quantities. So the first is summation k varying from 0 to n choose k times 3 to the power k. So this is a very direct question. Okay, so we can write it in the form, we can just introduce 1 to the power n minus k. This causes no harm. But now this summation is exactly the binomial expansion of 1 plus 3 whole to the power n. Right? If you look carefully, 1 plus 3 whole to the power n, if we expand using the binomial expansion formula, this is going to be exactly this thing. Right? And so therefore this is equal to 4 to the power n. Okay, so the first one is 4 to the power n. So next, what about the second one? Okay, so for this you need to recall a very useful identity which we had discussed in the last session, that is r times n choose r. This is equal to n times n minus 1 choose r minus 1. So this is a very important identity and we had discussed the proof in the last session. So we will use it here. Okay. So here what do we have? We have k times n choose k. So if we use this identity, what shall we have? We have this thing. So k times n choose k is n times n minus 1 choose k minus 1. So now n by n to the power k, this thing is nothing but 1 by n to the power k minus 1. Right? Okay, so now if we just replace k by k minus 1, so notice that here in the summation k goes from 1 to n. Now when k is equal to 1, what do we have? We have 1 by n to the power 0 times n minus 1 choose 0. So what we can do is we can instead write the summation as in this form. Right. So instead of varying k from 1 to n, we are varying k from 0 to n minus 1, and here in this expression we are replacing k minus 1 with k. So here we have 1 by n to the power k minus 1, which becomes 1 by n to the power k, and here we have n minus 1 choose k minus 1, which becomes n minus 1 choose k. Okay, but now this form is again the binomial expansion of some quantity, right? So this thing okay, so we are just multiplying this with 1 to the power n minus 1 minus k. So then this is nothing but the binomial expansion of this thing, right? 1 plus 1 by n to the power n minus 1. If we do the binomial expansion, we'll get exactly this thing. Okay, so this is my answer. Okay, I hope it's clear. Okay, so the next question is very simple. It's asking us to count the number of functions from a set x to a set y, where x contains n elements and y contains m elements. Okay, so what do we have? So we have two sets, x and y. So x contains n elements and y contains m elements. So now what is a function? A function is just a mapping from x to y, such that, so the first element, so let the elements of x be x1, x2 up to xn, and the elements of y are y1, y2 up to ym. So what does a function do? A function maps each element of x to some element of y. So then let's consider x1. So since there are m elements in y, so a function can map x1 to any of these m elements. Similarly, a function can map x2 to any of these m elements y1, y2 up to ym. So that is each xi right? So for each xi, there are m possibilities for the function. So then what is the total number of functions? Okay, so for x1 there are m possible values for x1. Again for x2, again there are m possible mappings, and so on. So we have m into n, and this will go on for n times. So for each of these xi, where I goes from 1 to n, there are m possibilities for mapping xi. So the number of functions is exactly this, and this is nothing but m to the power n. Okay, so the number of functions from an n element set to an m element set is m to the power n. Okay, okay, so the next question, it asks that we need to count the number of compositions of n if any number of parts are allowed. So what does a composition mean? So this was covered in the third week's lecture by sir. So a composition of n is basically, so let me define this. Okay, so a composition of n into k parts is basically a k tuple, that is k positive integers whose sum is equal to n. Okay, so what the question is asking is to find the number of possible compositions of n where the number of parts can be anything. So the number of parts can be, so the value of k can be anything between 1 and n, right? Okay, so yeah, so then so what is the natural thing to do? The natural thing is to, for every possible number of parts, find how many compositions are there. Okay, so for some value of k, so k can be anything between 1 and n, so fix some value of k. What is the number of compositions of n into k parts? So this is okay, so the number of possible compositions into k parts is nothing but the number of positive integer solutions of this equation x1 plus x2 plus up to xk is equal to n. How many distinct positive integer solutions of this equation are there? And this is a very standard formula which sir has already covered in class. So this is equal to n minus 1 choose k minus 1. Okay, it's a well-known quantity, which, so you can go over the lecture notes. So the number of positive integer solutions of this is nothing but n minus 1 choose k minus 1. So then what is the total number of possible compositions of n? It's just the sum of this thing where k varies from 1 to n, right? So okay, and this thing is nothing but 2 to the power n minus 1. This I hope you know that. So n minus 1 choose 0 plus n minus 1 choose 1 and so on up to n minus 1 choose n minus 1, that is 2 to the power n minus 1. So this is the total number of possible ways in which we can write n as the sum of some numbers. Okay?
Sir,
Yes.
so we are not allowing 0 here, right?
No. It's positive. So whenever we talk about compositions, we mean positive integer solutions, and whenever we talk about weak compositions, that allows 0. So when we allow 0, it's called a weak composition, and when we consider only positive integer solutions, it's called a composition.
Okay. Yeah.
Okay.
Fine.
Yeah. Okay. So this is done. Okay. So this is probably the last question for today. So this says, so this is about the Bell numbers. So the Bell number is defined as the total number of partitions of this set, the set of the first n natural numbers. So the total number of partitions of this set is defined as the nth Bell number. So what does it mean? What does a partition of a set mean? So let's consider some example. So suppose n is equal to 3, let's say. That is, my set is 1, 2 and 3. So what does a partition of this set mean? It means we have to partition these 3 numbers into some sets, into some disjoint sets. So what are the possible partitions of this? Okay, so one possibility is you take the empty set and 1, 2 and 3. So this is one possible partition. Then maybe 1 and 2 and 3 together. Then similarly and what is left, yeah, this thing. So these are the possible partitions. So either you take all 1, 2 and 3 into a single part and the other part is empty, or you can partition it by taking 1 in one part and 2 and 3 in the other part, similarly the remaining 2, or you can take 1, 2 and 3 each in separate partitions. So the number of parts don't matter. So what we have seen is the number of possible partitions of this set 1, 2 and 3 is 5 basically. So which means the third, so n here n is equal to 3, so b of 3, the third Bell number, is equal to 5. Okay, so in this way, so what does the nth Bell number represent? So you have the set 1, 2, 3 up to n. So in how many ways can you partition this set? And the number of sets that you create, that doesn't matter. The only thing that matters is the number of ways in which you can partition this set. So as we saw, for n equal to 3, this value is 5. So what we need to show is that the Bell numbers satisfy this recursion. So the n plus 1th Bell number can be written as sum where k varies from 0 to n choose k times b of k. Okay, so we have to just show that the Bell numbers satisfy this recurrence. Okay, so just let's write it once. Okay, so this is what we want to show. So now, what is b of n plus 1? It is the number of ways to partition the first n plus 1 natural numbers. So we have 1, 2, 3 up to n plus 1, and we have to count in how many ways can we partition this set. So now consider any partitioning of this set. So this quantity, this number n plus 1, has to belong to some partition, right? So what we do is consider any partition. So this number n plus 1 should belong to one of the sets of this partition. So then we consider okay, so let's say this is my set. So this set contains n plus 1 and it may contain some other numbers, and the remaining numbers, they have been partitioned in some way. Okay, so this partition contains n plus 1 and it may or may not contain some other numbers, and the remaining numbers have been partitioned in some way. Okay, so now let's say the total number of elements present in all of the remaining sets, let's call it k. So let k okay, so we let k be the number of integers that do not belong to the set which contains n plus 1. That is, the total number of integers present in all of these sets is equal to k. So what can we do? First of all, let us select these k integers which will not be with n plus 1. So these integers, so we have the n integers 1, 2, 3 up to n. So out of these n integers, there will be k integers which do not belong to the partition that contains n plus 1. So first of all, let us select these k integers, and that can be done in n choose k ways. So Okay, now once we have selected these integers, there are remaining n minus k integers, and those must go into this particular set which contains n plus 1 by definition. So once we have selected the k numbers which will not be with n plus 1, the remaining n minus k numbers which we have not selected, they must be with n plus 1. So okay, so what we have done essentially is we have already fixed that particular set which contains n plus 1, that is already defined. So once we have selected these k integers, the partition that the set that contains n plus 1, that is already fixed. Why? Because that particular set is going to contain n plus 1 and the remaining n minus k numbers. So that partition is fixed. Now these remaining k numbers which we had initially chosen, so they can be partitioned among themselves in b of k ways, the bell number, the kth bell number. So okay, okay. So in total this gives us a partition of the numbers 1 2 3 up to n plus 1, right? This gives us a partition. So now this k can be anything between 0 and n, right? The number of integers which do not belong to the partition containing n plus 1 can be anything between 0 and n. So hence, what is b n plus 1? The number of ways of partitioning. So this is, you take the sum from k is equal to 0 to n. In n choose k ways, you select the first k numbers which will not belong to the partition containing n plus 1, and then partition these k numbers in b of k ways, right? So this is going to give the number of ways of partitioning the first n plus 1 natural numbers. Okay, so hence we are done. Okay, so yeah, so that's it. So if you have any questions, you can ask me, else that's it for today. I will be sharing this recording and this notes with you, don't worry. But yeah, if you have any questions, you can ask me. Okay, so if not, then we can close. All right, then bye everyone.